All right, let's take a look at a very simple parallel circuit, an introduction to parallel circuits. I have a total applied voltage in this circuit, as we can see, at 120 volts over here. And I have a resistance. Resistor number 1 is 10 ohms, and resistor number 2 is 10 ohms. So the first thing I want to do is I want to draw my current paths here so we can see how my current paths are going to work in here. We're going to go from negative to positive. So my current must go through here, and then it must go down this branch. And as well as going down that branch, it's splitting, and some of that current is going through here and goes down that branch. And then, of course, the current goes through that load resistor and comes back and combines with the load that's coming down from here and goes back home. So I'll put the polarity in here. I'll put a positive over here and a negative over here. Now what we want to do, the first thing we want to do is find our total resistance. And to find our total resistance in a parallel circuit, there's a couple of ways that we can do it. We can use product over the sum, or we can use a reciprocal over the sum. Since we only have two resistors, I'm going to show you the product over the sum. And the calculation for that is the total resistance is equal to resistor 1 times resistor 2 divided by resistor 1 plus resistor 2. So if we're to input those values, we'd have 10 times 10 over 10 plus 10. So of course, we've got 10 times 10 is 100, and we've got 10 plus 10, which is 20. So we've got 100 divided by 20, which is 5 ohms of resistance. Now you may be thinking, well, how is it that I have two resistors in this circuit and my total resistance for the circuit is less? Well, it's very simple actually, and the way I want you to think of it is, if you're driving down the highway and there's a car accident, and all of the roads to get off the highway are closed because of this car accident, and all that traffic builds up. So all the flow has to go through this car accident. But all of a sudden, the police open up a road and you can start driving down that road. Now there's an additional path for you to drive down. So if there's an additional path for you to drive down, such as this branch circuit here, then all of a sudden the amount of resistance to that current flow has decreased because another path has opened up. So in a parallel circuit, when you're looking at the total resistance must always be less than the smallest individual resistor that's in parallel. So if we want to know that we're on the right track here, we can say, well, yeah, so my total resistance in this case is 5 ohms. And each individual resistor is 10 ohms. 10 ohms there and 10 ohms over here. So it sounds right. Now, another way to sort of shortcut to get my total resistance in here is that I can actually say, well, you know what? I have two resistors. And they're equal value, those two resistors. So they must split the current equally. But this only works if they're equal value. So I have 10 ohms divided by 2 gives me a total of 5 ohms. Okay? So there's a couple ways to do it. The important thing is to understand why it's happening. Okay? So and the reason that it's happening, that the resistance is lower, is because you have more paths for current to flow. So if you have more paths, then you have less resistance overall. So let's write in our total resistance of 5 ohms over here. All right, so now that we have our 5 ohms, we have 120 volts, we'll be able to find our total current using our Ohm's law. So my current over here, so I want to solve for I. So I is equal to E divided by R. Well, let's take a look. So my I total is going to be equal to my voltage of 120 volts divided by my resistance of 5 amps. So 120 divided by 5 gives me 24 amps. All right, let's finish off with our totals here. Let's get our power. And if we go back here, we look at our power. Our power is equal to my voltage times my amperage. Well, let's take a look. So my voltage here is 120 volts, and my amperage is 24. So 120 times 24 is 2,880 watts. All right, so now we've got our totals here. Now we can start taking a look to see what we want to do for our voltage here. Let's take a look at our voltage for resistor 1. In my earlier videos on series circuits, the voltage divided, because a series circuit is a voltage dividing circuit, and the current stayed the same, or the amperage stayed the same, because it had to flow through all that one resistor, or all the resistors that are in series. In a parallel circuit, the current divides. It's a current dividing circuit. So your current is going to divide, but your voltage is going to stay the same. So just to sort of prove that point, if I was to look at this point here and this point here, I can see, well, this point here and this point here is really the same as this point here and this point here, and that total is 120 volts. There's really no difference between those 2 points. There's no series resistor dropping any voltage. That's the same as this point here and this point here, and therefore that is the same as this point here, and really it's the same as it is here, and it's the same as here and here. So really we can see that those are just extensions of that wire there. There's nothing in between them. That's just the extension of that voltage power supply wire. So we can say that our voltage is 120 volts here across that load, and our voltage is 120 volts across here, across load resistor 2. So that's fairly simple. So we just go on the basis that in a parallel circuit, voltage remains the same, but current divides. So let's take a look at our individual current dissipations here. So our individual current divisions here are going to be, well, if I want to know what my voltage is, let's take a look over here. My amperage. If I want to know what my amperage is in this circuit here for resistor 1, I can say, well, my amperage is equal to my voltage divided by my resistance. So my voltage divided by my resistance, 120 divided by 10, is going to give me 12 amps of current through here. Now, if I want to say, okay, well, let's take a look at this one here. I've got this exact same values over here. My amperage is my voltage divided by my resistance, so I can have the exact same amperage here. Now, Kirchhoff's current law, Kirchhoff is Kirchhoff's current law and Kirchhoff's voltage law. The current law says that the individual branch divisions of current must equal the total current in the circuit. Really what it says is that, you know, all the current going in minus all the current going out must equal 0. And we sort of look at it as going, well, what's going in must come out. So if I've got 12 amps that's coming through this branch, I can see that I've got 12 amps cruising through this branch right here. And then I must have another 12 amps that's going through this branch here and through here. So I can see that I've got 12 amps that's cruising through here. And that 12 amps comes along and meets up with this 12 amps. So at this point, I'm going to have 24 amps. If I was to install an ammeter right there, I'd see I'd have 24 amps. And if I was to install an ammeter right here, I would see that I would have 24 amps as well. So my individual current divisions equals my total current in the circuit. So that makes sense. All right, let's do our power dissipation in the circuit. So my power, total power, we have 2,880 watts. And my power in 1 is going to be equal to my voltage times my amperage. My voltage, 120 times 12, is 1,440 watts. Well, let's take a look. 1,440 watts is exactly half, isn't it? It's exactly half of 2,880 watts. And the reason that it's exactly half is, well, because the voltage is 120 volts. The amperage is exactly half of the total amperage in the circuit. So the individual power dissipations are going to divide equally. So I can say that over here I must have 1,440 watts as well. And you can check that. 120 volts times 12 amps is 1,440. So I've got 1,440 watts here, 1,440 watts there is 2,880 watts. So it works out.